All right. Chapter 10, homework numbers 3 and 4. What I checked off? Good. So I'm in the right section. I started writing your test yesterday at a very boring meeting. I got 3 questions done. I will continue writing your test today at another boring meeting. And I think by the time I'm done, your test will have 6 questions altogether. So maybe 7, because I think I might even throw 1 multiple choice problem on there too. So that's good and bad. The fewer the questions, obviously, the more we feel like you got to get them right because each one's worth more points out of a 100-point test. But as long as you're showing your work, like I'm about to do on questions 10 through 12, then you know that you're going to get good partial credit points. And therefore, don't think of it as just being 6 or 7 or 8 questions on your test. Think of it as each problem is really like 10 points on its own, and you just have to start getting some parts of this correct. I've started getting a few of the labs already, and they're good and bad, but one of the things that I see that's bad is that some people are choosing not to show very much work. And if you don't show your work and you don't have the right answer, right? Everybody should have the same answer for the 0.19 grams of lead. If you don't show your work, I can't, on the test, I can't give partial credit. So, and then if you try to like shortcut the work, I also can't give as much partial credit. So with so few questions, please show your work. All of these feel like math questions. Therefore, we're going to start by drawing ourselves a nice long conversion table line, a question mark, and then we're going to go find a question somewhere in there. A few of your test questions are this easy, where we'll start with what is the mass of, what is the number of moles, how many molecules are there, what is the volume. But then there's also a couple questions where it will be kind of embedded in the center of the problem. Like one of them says, in lab 10.1, you may have, and then goes da 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 da. So you have to look around and see if you can figure out from the context of the problem where the question is. Once you find the question, put the units of whatever it is they're asking as what you're trying to answer, right? So what is the mass of sulfur dioxide? So I'm going to put grams of SO2. And then I'm going to take the number that they gave me, 2.11 times 10 to the 24th power molecules, as my starting point. Boy, that feels very much like a test question, but they all do, don't they? Right? I mean, there's not that many different ways I can ask the same things over and over again. SO2. All right, savor your molecules for a moment because we're just as quickly going to get out of them. They're going to go away. Molecules of SO2. Okay. And then in this class, I would love to go straight into grams. I would love to put grams at this location right here. But the problem is there isn't a conversion straight from molecules to grams. You can make one up. You could combine your periodic table with your Avogadro's number, and that technically would be correct and it would give you the right answer. But if you get anything wrong and you do that, you risk losing partial credit, because that is not the way I taught you. And not that I'm so special, but what I am teaching you is the classic way that chemistry students are supposed to solve conversion table problems. You get out of the unit that they give you and you get into moles. A 1 always goes with the moles, and then you have to decide what you're going to put with molecules. You have 3 choices. You can use 6.02 times 10 to the 23rd, you can use 22.4, or you can use your periodic table. And so it's your job to know when do you use which one. In this case, it is the 6.02 times 10 to the 23rd. I just graded a lab from somebody that's in the other period. And when they were doing maybe the last step of the first of the virtual lab problem, all they wrote down was just the 6.02. They didn't bother writing down the times 10 to the 23rd power. I'm not going to give the same partial credit to that. It is supposed to be 6.02 times 10 to the 23rd, right? If I went up to Mr. McCall's office and said, hey, I'm a little strapped for cash right now. Can I get my paycheck a little early this month? And he goes, sure, I don't even know when I get paid because my paycheck just goes straight to my wife, and then she puts it in the bank and spend, does whatever she does with our money. And then I just, every once in a while, I'll say, hey, can I have a little bit of money? And then she gives me a little bit of money. So I don't really know what I make. Let's just pretend that I make $5,000 in a month. That sounds like a good amount. What if Mr. McCall says, okay, here you go. Here's your $5,000. Wouldn't I be kind of like, well, wait a minute here. That's $500. There's a difference between those two things. That extra zero matters. That times 10 to the 23rd is a whole lot of extra zeros. Don't leave it off. If I don't see the numbers written correctly, if I don't see the units in the conversion table steps, I will not give you the same partial credit. And since this test is a take-home test, I'm not going to give you, if all I get is just the answer and there's just some scribbling here without showing me the work correctly, you're not going to get even full credit. Whereas in a normal class setting, I would give you full credit if you just had the answer, because then I know you can't look at your notes. So I know there must be something going on inside your head. Now I don't know that. So show your work. I can show the work. There's only 6 to 8 questions on your test. Show your work. What we have effectively done right now is gotten out of molecules of SO2 and gotten into moles of SO2. That's not what we want as an answer. So I am going to continue this one more step and get out of moles of SO2 and get into grams of SO2. So I go to my periodic table and I add 1 sulfur at 32.1 plus 2 oxygens is 16 and 16 more. I think gives us a total of 64.1. Those of you keeping track of the units, those cancel out and we're left with grams of SO2, which is what I want. And my calculator says 224. Okay. Question number 11, what is the mass of? Feels like a math problem. So we will draw a conversion table line, equal sign, find the question, what is the mass of? Iodine, so far on your chapter test, what I've done, because one of the forms of the test does have iodine as a question, is when I wrote the word iodine, I put it like this: iodine, comma, I2, question mark, so that you know that it's diatomic. I haven't finished the whole test, so maybe further on in the test, there might be a situation where I don't list if it's diatomic. But so far, I have put that on there. So if you don't add 2 iodines together, of course, it's going to cost you. Problems like this one where it says sulfur dioxide, I didn't do that. I expect you to be able to come up with chemical formula. You know, simple ionic compounds, you know, sodium chloride, potassium fluoride, calcium chloride, those kinds of things, I expect you to be able to come up with chemical formula for them. If you can't, don't quit on the problem. Keep working it out. The only thing that's going to be wrong is your mass step will be incorrect. But that doesn't mean that you're not going to still get a good score, because part of the score of this is you showing me that you know how to swing. Remember, like we talked about Luke Skywalker when he's on that little planet with Yoda, and he's just teaching him how to use a lightsaber, right? It's the fact that you can show me the steps, even if one of the steps is wrong, you still show the steps all the way through, even if deep down inside you know you've done something wrong. 1.02, or no, 1.0 times 10 to the 22nd molecules. You don't have to include the substance. I told you I wouldn't mark that off, so I'll just leave it out for right now. Savor that, because we're now going to get out of it. Molecules of whatever the substance is, and because we can't go straight from molecules to grams, we're going to go towards the mole. 1 mole is 6.02 times 10 to the 23rd molecules. And then my last step here, because I don't have what I want as an answer yet, I'm going to get out of moles and I'm going to get into grams. This is where it'd be nice to know what our substance is, because otherwise, you know, what are we going to put? Now on your test, if you don't put that, but you have written down here the correct number for the grams for I2, I know what the correct, I kind of know what the correct number for grams of I2 is. It's a lot, right? And of course, I'll make an answer key, so therefore I should have this, this number there, but you're going to add 2 iodines together. And I guess now I'll just go through and put an I2 by every one of these steps. And periodic table is going to tell me that number, and then a calculator is going to tell me this answer. 4.22 based on 253.8. Significant digits. This only has 2 significant digits. This should only be 4.2 grams of I2. And I am doing that on the test. So far, in the 3 questions that I've written, 2 of them I put 3 significant digits. 1 of them I put 2 significant digits, and I expect to see the same thing in the answer. My guess is tonight when I'm writing question number 4, I'm going to put 4 significant digits so that I expect to see 4 in the answer. I've been told that I made a mistake on number 12, so please forgive me if there is a mistake here. You don't need to write down the compound other than the fact that you have to have the correct mass if it's a mass problem. So if it's just grams and liters, right? Or no, not grams, because grams is when you do need to know it. But like if it was a problem that went from molecules to liters, it wouldn't matter what the substance is, right? Because every substance is going to use this number here, and every substance for liters is going to use 22.4. So it's only the mass is where the substance matters. But if you don't write it in the problem, but you have the number, that's fine. You do need I2, because if you don't use I2, you wouldn't have put 253.8, you would have put 126.4 or something like that, right? So it has to be I2, but you don't need to write it in the answer. No, if that's all you have for the problem, if you just write it like that, you will get full credit, full credit. How many molecules is 126.7 grams of sucrose? All right, I've had a few people tell me that I did this one wrong. So let's see what I did wrong. So first of all, what I know I'm going to do right is I'm going to put my question over here. Feels like a math problem, so I do converge table 1. Molecules of sucrose right here. And then I'm going to take the 126.7 grams of sucrose, put it right here. Then I'm going to get out of grams of sucrose right here, and I'm going to get into moles of sucrose right here. Then, those of you keeping track of units, grams will cancel out. So my next step is I'm going to get out of moles of sucrose right here, and I'm going to get into molecules of sucrose right here. Then I'm going to put in 6.02. Nah, I'm not. I'm going to be, sorry, this is going to be a little bit sexist. I'm going to be like a lazy teenage boy, okay? I know, to say lazy teenage boy is kind of redundant, but lazy teenage boy. And here's what I'm going to do. I don't feel like getting my calculator out. So I'm going to say that this number right here is 126.7, and I'm going to say this number here is 126.7, and put a 1 and 1 in here, and then my calculator says that cancels out with that cancels out with that cancels out with that, and my answer is 126.7 molecules of sucrose. Hey, teach, how many points do I get for that? You get a lot of points for that, because number 1, the conversion table is correct, right? What's in blue besides the numbers is all correct, and that's the most important part to me. The only reason why I would take off points for these 2 steps right here is because step number 3 is not showing me that you know that molecules mean 6.02, right? In fact, I don't know, why would I even use that? Even a lazy teenage boy is not going to put 126. Why not just put 6.02 times 10 to the 23rd? Because you still don't need to use a calculator, because you can just say this answer is 6.02 times 10 to the 23rd, right? So now that step doesn't even lose any points. So the only thing that's losing points is the fact that you don't know what the mass of sucrose is, because you don't know what the chemical formula for sucrose is. That's a minor loss of points on your test. I would say with the curve, you're probably going to, especially because of showing all the work so nicely, you're going to still get over 100% on your test, okay? So it's not that big a deal. Now, let's see what I did wrong, because I've been told by a few people that I did something wrong. I've been told that I put glucose here, which I did put glucose, right? Sucrose is C12H22O11, I think, and I wrote this all the way through with glucose. Now, I do know this. Last couple of years, I fixed this, so this doesn't show up like this. But when I remade the notes, I'm still using an old set of slides that I remade the notes with, and it snuck through the problem. I had just changed this to glucose, and it didn't change. So yeah, you're right. I made a mistake. I have the wrong substance that is there. But okay, let's use this as another learning tool. What happens on the test if I say to you, how many molecules is 126.7 grams of sodium chloride? And you write down that the formula for sodium chloride is SCl, because you think for some reason that sodium is sulfur, right? Because it starts with an S. And so then you add together 32.1 plus 35.5 and solve this using 67.6 grams per mole, right? how many points should I take off for that? You messed up on something from chapter 9. You didn't mess up on something from chapter 10. So it's not that big a deal. That's just me covering my own mistakes. Okay, that was number 12. Question number 13. All right, 13's weird. I'm going to go to the next slide right away so we can see my picture that I've drawn here. And we can explain a concept in chemistry that's an important concept in the future. 3 balloons each contain the same number of molecules of 3 different gases at STP. What we know is at STP, 1 mole of every single gas occupies a volume of 22.4 liters. So if these were really large balloons and they could contain exactly 1 mole of gas, all 3 of these balloons would be exactly the same size. But what we notice is that the carbon dioxides are much bigger molecules than the hydrogens. Hydrogens are really small molecules. They only have 1 energy level. There's 2 of them attached to each other. Their total mass is only 2 grams per mole, 1 plus 1. Whereas if you look at the carbon dioxides, their mass is 44.0 grams per mole. Oxygen's 32.0 grams per mole. And hydrogen is only 2 grams per mole. All right, so if you could take these balloons and weigh them, what you would notice is that a 1 mole balloon, each of those balloons would have a different weight. Each of those balloons would have a different mass, okay? And you can see the numbers that are there. But each of those balloons would be the same size. And that doesn't seem right, because you would be thinking, well, shouldn't the larger molecules occupy more space? The truth is they don't, because when we really think about this on the atomic level, the size of the molecule is so small compared to the size of the balloon, right? 22.4 liters. Remember, a 2-liter Coke bottle, how big that is. Picture a 2-liter Coke bottle that was 22 liters big. That would be a large Coke bottle. Those little atoms in there are so small that at the atomic level, the carbon dioxide molecules and the hydrogen molecules really aren't that much different in size, okay? Now, what makes a balloon keep its shape is the fact that the stuff that's inside of it has to be colliding with the walls of the latex, of the rubber, in order to keep the balloon so that it keeps puffy, right? So how do they do that? They do that by slamming into the walls as hard as they can. Hydrogens, being smaller, don't collide with the same mass force that the carbon dioxides do. So bigger, dopier carbon dioxides collide with the walls of the latex and keep the balloon outward. So what hydrogen does to make up for that is it travels faster. So it has a higher speed. What we're going to learn second semester is if all of these are at the same temperature, right? Standard temperature and pressure, they're all at 0 degrees Celsius. Then what we find out is temperature is basically measuring, that's a squiggly line that means that it's proportional to kinetic energy. Kinetic energy is the energy of motion. It has a formula called 1/2 mass times velocity squared. So big, huge carbon dioxides have less velocity. Small little hydrogens have more velocity so that they all have the same kinetic energy. Therefore, they're all at the same temperature, and therefore they all take up the same amount of space. Good times, okay? But they have different masses. So anyway, not that you need to know this for this chapter, but that's good chemistry. That's the kind of stuff that if you're going to walk away from a class like this, I don't know, there's just stuff you should know. 14. Assume the following gases are at STP. What is the volume? The first 2 questions on your test are simply switching between one of your 3 units and moles, right? So you'll get one question that says, what's the volume of this number of moles? And then you'll get one question that says, what's the number of moles in this volume? And then switch that up with grams and molecules. So everybody's going to get 2 2-step problems, and then everybody's going to get 2 3-step problems, and then everybody's going to get 1 multiple choice question. I'm making this up as I go right now. And then everybody's going to get 2 of the questions that we start learning about in the second half of today. What's the volume? Sounds like a math question. Draw yourself a conversion table line. Write down the units of whatever the question is. Volume means L for liters. Carbon dioxide. I like to include the substance, but that's because I'm a teacher. I get paid to do this. I just don't know how much. 3.20 times 10 to the negative third moles of CO2. Savor it because you're going to get out of it. Get out of moles of CO2, get into liters of CO2. At STP, 22.4 liters. I'm going to hurry through this because every one of these is the same. And if you don't understand it, you should ask me in an email so that we could go over a problem like this together and make sure that you understand it. If you are just copying my slides, shame on you. You need to spend the time to work the problem. If you're not showing me your work, shame on you, because then I don't know what you know, right? You're possibly just turning in a homework assignment to me so you can get those 2 measly points when you've got this 100-point test looming out there. Show your work so that I can see what you're doing, so I can then write back in the email to you. I can say, hey, on step number 2, you have your numbers backward. You put the 22.4 with the moles and the 1 with the liters. And then you can learn from that mistake. Notice how I show all my work. On the test, you're going to be required to show the work besides just getting the answer correct. Question number 15. Going the opposite direction. Let's skip right down to letter C. The reason I'm skipping down to letter C is because this is how I don't try to throw you off, but what happens is sometimes I catch those kids that are we would classify them in the smart category, but they haven't tried super hard during the chapter. And then a problem like letter C comes up and then they make a mistake. Here's the mistake. What is the number of moles? Okay. They know to put moles. They might even want to put the fact that it's ethane. All right. Then they put the number that was given, 1.00 times 10 to the third power liters of ethane. Here's where this mistake occurs. They saw scientific notation, so they feel compelled, even though they know to put the units, C2H6, get into moles of C2H6. Because they saw scientific notation, they jumped to 6.02 times 10 to the 23rd. Don't do that. You don't base what number you put based on what number I give you. You put what number based on being a young Luke Skywalker, based on the fact it says liters. If it says liters, you have to put the conversion unit that deals with liters. So no to 6.02, 22.4, and a 1. And the 22.4 follows the liters to the bottom. A 1 always goes with the moles. Look at this nice and clean and neat. Let's try to see if I made any mistakes. Like, for example, 3 significant digits and the units, no mistakes. I feel good about all that. You let me know if you see a mistake. Question number 16. At STP, what volume does 12.2 grams of fluorine occupy? So, feels like a math problem. Conversion table line. What is the volume? If you don't know the units of volume, write me volume. Okay, that's worth something, but we'll use an L. All right, put your first number on the first line. And then this one here, we run into that issue with fluorine. So if you write down F for fluorine and you work this entire problem out by getting out of grams of fluorine, getting into moles of fluorine, put a 1, of course, there, getting out of moles of fluorine, getting into liters of fluorine, 22.4 and a 1, you're a good person. Here's the issue, is at this step right here, because you saw fluorine and you picked F, you put 19.0 right there. Well, that's not completely true because fluorine's part of our, and I'll goodbye to you this morning, right? We have to always make sure that our diatomic elements are always, when they're by themselves, are always traveling around in a group of 2. Hanafokobrai to you. The F is one of them. So therefore, this is not 19. Instead, this is 38. Now, what if you make that mistake on your test? Well, on the in-class version of the test, you don't lose any points. The person who puts F2 actually gets an extra credit point. On the take-home version of the test, since you can use your notes, you're going to lose a point if you don't do that. But still, That's not enough to hurt your score. You should still get an A. You should still even possibly be able to get over 100%. Looks good. 3 significant digits, 3 significant digits. My units are in the answer. Question number 17. Feels like a math problem. Hey, here's one where it doesn't matter that it's argon. This is what, if you were reading the chat and you saw what Nick and I were saying back and forth, this is what the one that I was referring to where you wouldn't need to put the substance. I didn't understand that he was just trying to say it doesn't matter in the final answer. Both of us were correct. What volume? Oh, and here's another one, is the question is kind of embedded in the middle of the problem. You have this many molecules, what volume do they occupy? I'm sure that on the homework sheet, this is written out as a better sentence. Volume means liters. All right, so we're gonna start with our given, 13 times 10 to the 24th molecules. Like I said, I'm not even gonna put the substance this time. Get out of molecules. Get into moles. You see that I keep fighting it. I write molecules and I can't help, but my pen just wants to keep writing and put the AR at the end of it, right? It's like a baseball batter that's up to bat. When you go to swing, you don't stop swinging just because your bat made contact with the ball. You continue swinging all the way through. It's called follow through. It's what makes one batter a better batter than another batter, right? It's what makes one chemistry student a better chemistry student than another chemistry student, is by follow through, by putting the units. But we're or by putting the substance. But we're trying to show that on this particular problem, if you didn't do it, it doesn't matter what substance this is. 6.02 times 10 to the 23rd molecules of unknown substance A. Last step, get out of moles of unknown substance and get into liters of unknown substance. That's another constant. So no matter what substance this problem is, everybody's test gets the same answer, right? If everybody has this number, everybody has the same answer. Nothing there that needs argon, but I put it in because it's just good follow through. And some of you do really, really exemplary work. The stuff that gets turned in, I look at your work, I'm just like, oh my gosh. I mean, I'm sorry. So if I call out some people and not other people, then you're going to be mad that you didn't get called out. But I know ones that I graded today, I feel like the very first homework assignment I looked at today was Janelle's. Your writing is perfect. It could be a font. I remember later in the day, Ezekiel's, your writing is perfect. It could be a font. They could make it a font on Google Docs. I probably would say the same thing about Ashley's, except for that instead of me having her look at her homework assignment, she always just points out all my mistakes. And so then, I got to go back and fix all my mistakes. But same thing, exemplary work. I think this is the other one that I made a mistake on, huh? Feels like a math problem. What is the mass? Get into grams. I've been told that I wrote down fluorine, which means I cut and pasted number 16 into number 18 and didn't change the substance. Grams of carbon dioxide. We're going to start with 2 liters of it. It does matter that it's carbon dioxide here because if mass is mentioned, periodic table is coming into this one, huh? I don't know what that means, but I started to write a note. Maybe I even put it into the response on her email and she's not the only one. There's a few of you that what I should do second semester is maybe like over winter break, I should pay you to write my slides for me for second semester, or maybe at least go through the slides I already have written and just find the little ticky-tack mistakes I keep making and fix them for me. That's what I used to have TEs, you could put he, and I put TE. That's what I used to use my TAs for, was to fix my mistakes. But usually TAs, they don't find the mistakes either because they don't care enough, right? They want to get to their own homework or whatever else they're doing. You started with liters, savor it because you're going to get out of it in step number 2. 1 always goes with the moles. Liters is special. It gets that number 22.4. All right, those of you keeping track of the units, the liters cancel out. We're in moles. Now we're in moles. Let's get out of moles and let's get into the units of the final answer. Periodic table says 1 carbon plus 2 oxygens is 44.0. Didn't come out very good. Let's try it again. Try it again. There we go. 44.0 grams CO2. Okay. I don't need to see the work. I probably have it on the next slide though. Nope, I didn't show my work either. If you don't do the whole 1 carbon at 12.0 and 2 oxygens at 16 each, add those numbers together and show me that's 44. I'm not going to mark that wrong if you don't do that. But if you get the answer wrong, then that would count towards partial credit. And yes, right there, typo on my part. Cutting and pasting, I guess that'd be my only explanation. Probably not even cutting and pasting. I was probably watching TV while I was doing this and something good happened. Like I was probably watching the Tour de France, you know, people pedaling their bicycles for 6 hours straight and they filmed the whole thing. Like, ooh, that person just switched gears. Ooh, that person just pulled over to take a potty break, right? Those kinds of things. Those are exciting days in the Tour de France. All right, today's notes. Today's notes are kind of just like well, there's two things going on here. There's some practice with what we've been doing, and then there is a new section that we're going to cover today that is important. So we'll get to that. It's kind of boring doing these same problems over and over again. That's why it's nice when it's in regular school, when we're just here for 1 hour, that this would be then what we do. Because right now it almost feels like let's skip over this and go straight into the next set of notes, which are new. I can't do that because there's people in this Zoom room right now that didn't really do their homework to the extent that they should have. There's people that didn't do their homework, period. And so if we don't go over some more practice problems, we might have those people get left behind. And that's not the way education works. We're supposed to try to bring everybody up. So I'll give you a moment to copy those down. Maybe while you're doing that, I'll take a roll. Times like this is usually when we talk about other stuff. Like for example, in first period today, somebody asked, when do you think, have you heard anything more about us coming back to school? And I said, no, I haven't. But I do want to say this to all of us. If we want to go back to school, this next week is a critical week because next week begins the time where we start going and meeting our family that we don't always see for Thanksgiving. And if there is a continued spike in COVID cases like is going on right now, we're going to risk us being able to go back to school in January. And I don't think most of us want that. Some of you may be like, yeah, that's cool with me. Well, that's okay because you can still stay at home. But those people who want to come back to school, we want to be able to come back to school. So try to set an example for your family. Wear your mask. Don't go hug your grandparents. Stay away from them. Say, sup, grandpa, right? And then maybe next year you can hug them or give them a virtual hug. Give them a heart from the distance, right? But if you're going to be forced by your family to meet with family, do everything you can to make sure that everybody does the masking and the social distancing, because if we can bring our cases back down, they'll let us come back to school. They made me get lost on where I was. Griselda, Genesis. You're going to ask for a lock, like a lock for your room to keep people away, out. All right, I got to Allison, so I'm going to stop with roll so I can get going here so you guys don't have to wait. One copper cylinder from a lab had a mass of 57.68 grams. How many copper atoms is this? If you're sitting there going, oh man, I missed out on that lab. No, you didn't, because the lab that this is describing is the same one that we sent home for an at-home version of the lab. In fact, in some respects, I feel like this is almost a better lab than the in-class, because you're able to use your own stuff. It's not like it's just this abstract school stuff that we play with. It's actual your stuff that you have around the yard or the house or the garage. And it's like, wow, I've got this piece of copper. How many molecules are in there? How many atoms are in there, right? So that's the idea. I agree with you, Allison. It just doesn't seem worth it, especially when there's going to be more Thanksgivings in the future. More than that is, you could have a half-year Thanksgiving. Is once the vaccine is out, there can be a Thanksgiving for April, right? Let's call it a different holiday. Maybe this will be the year where we have the biggest Cinco de Mayo parties we've ever seen, because by then we know for sure everything's going to be back to normal. And so everybody's going to just have just a tremendous amount of energy they want to let loose. And then it's okay, because we're not taking any risks in terms of COVID. Obviously, people still die in drunk driving accidents and things like that. So, you know, there's lots of places where we have to do the right thing. How many copper atoms is that? Sounds like a question. Atoms of Cu. 57.68 grams of Cu. Savor it, because immediately we're going to get out of grams of copper and we're going to get into moles of copper. I did not head straight into atoms. We don't have a conversion straight from grams to atoms. So you have to go through the periodic table. 63.5-ish. 63.5. I think I remembered that number because yesterday somebody's form of the test had that. So let's be ready. Get out of moles of copper and then get into atoms of copper. And a 1 always goes with the moles, and a 6.02 times 10 to the 23rd atoms. And then we solve. Did I make answer slides? I did. Hey, look at that. 5.47 times 10 to the 23rd. Significant digits. I blew it. Mr. Purser just lost 1 point on this question. 4 significant digits, so I've got to actually work this one out. 57.68 divided by 63.5, and then times 6.02 times 10 to the 23rd, 5.468. I have a hard time with significant digits on a problem like this because of these 2 steps right here. A student that was to say, I'm going to put 3 because these only have 3, technically is making a good point. So I probably would let this one go. I'll avoid that. I don't know what you guys mean by next Thanksgiving isn't guaranteed or graduation isn't guaranteed. I mean, of course, in terms of you personally, we don't know. There could be, this is partly why we're so happy that our pharmaceutical companies are coming up with vaccines so quickly, is because if we can bring COVID-19 to an end quickly, we don't provide it an opportunity to mutate, right? If it no longer can find hosts, it can't survive. And if it can't survive, it can't mutate. And what it mutates into, you know, could be worse, could be more communicable, could be more deadly, could be harder to make a vaccine for it. So of course, nothing's guaranteed. That's why you have to savor every moment of your life, the same way you savor the given in a problem before you move on and get rid of it in the next step. What mass is this? Grams. Dinitrogen monoxide. Dinitrogen N2 monoxide O. Now here's a perfect example of if you make a mistake on your test with the chemical formula, but you do everything right, I'm not going to take off much points. Start with your given, 2.0 liters of N2O. Get out of liters, get into moles. I would love to go straight from liters into grams and make this a two-step problem, but you guys are starting to recognize the theme of this class. Everything passes through the mole. If it's your final answer, it's a two-step problem. If it's your given, it's a two-step problem. But if your given and your answer are not moles, it's a three-step problem. 22.4 liters is 1 mole. Now we're in moles. Let's get out of moles and get into grams. Periodic table says 2 nitrogens at 14 each is 28, plus an oxygen is 16 more. I think 44. Let's see what the next slide says. 44. One more, then we got to talk about new stuff for today. Hydrogen sulfide is a dangerous gas released in volcanoes. If the scientist collects 10 milliliter sample of this gas at STP, how many gas particles are present? Turns out that this problem, we don't even need to know what the chemical formula for hydrogen sulfide is, and we'll still get the answer right. How many gas particles? Fine, I'll write particles of sulf, because I don't know what his chemical formula is. So then in step number 1, 10 mils. Now there could be a mistake because we don't do anything with mils in this chapter. We need to change that to liters. A reminder to you that King Henry David usually drinks chocolate milk. And so if you want to go from milli, you're going to go 3 places to the left with your decimal. So it becomes 0.010 liters. Don't let something like that get in your way. If you know it's wrong, don't quit on the problem. Just work with it. Use it the whole way through the problem. It's not the end of the world, and it's definitely not going to hurt your grade much. I don't know what hydrogen sulfide is, so I'll just leave it out. I'm going to get out of liters of hydrogen sulfide, and I'm going to get into moles of hydrogen sulfide. Okay? Doesn't matter what it is. Every gas at STP is 22.4. Okay, so liters canceled out liters. Now moles of this unknown stuff, we're going to get out of moles of this unknown stuff. If we have to get into grams, then we need to know what it is. But if all we're doing is going into number of particles, I'm going to use my Avogadro's number, 6.02 times 10 to the 23rd. Now, what is hydrogen sulfide? Well, hydrogen's in column 1, so that makes it a +1 charge. Sulfur's in column 16, that makes it a -2 charge. Crisscross those oxidation numbers and you're going to get H2S. So I don't want you guys to think, well, he doesn't even know. We're being taught by somebody who's a complete moron. Not a complete moron. Okay, and the answer, 2.69 times 10 to the 20th particles. If you like what I see, 3 significant digits, 3 in the answer, units are there. One more section to cover, and then we're all done for today. I'm going to move forward. All right, so in experiments, it turns out that in experiments, when they do something called calorimetry, that you could actually take hey, look, there's glucose again. You could take a substance like glucose and you could actually heat it. You could either combust it, burning it with oxygen, and look at the products, carbon dioxide and water that are formed, which are really easy to separate. You just got to cool it down. If you cool it down, the water will condense into a liquid and the carbon dioxide will be separated from it, and you could weigh those. And you could use that to figure out what the chemical formula of glucose is, okay? You could decompose it. You could heat it to the point where the glucose actually will release carbons and also release waters. And in fact, this would be something that I'll do as a demonstration for you second semester when we come back, is that we can do this and make what's called the carbon worm. And you could separate it, okay? So in other words, the point of this is if you have a substance that you know is made of carbons, hydrogens, and oxygens, which could be any one of those sugars or the backbone for the, what do you call them, saccharides, that you could take all of these and you could figure out their composition by doing experiments. So this section is kind of related to that with the experiments. All right, we call it percent composition, and you're going to have two problems on your test that basically go backwards of each other. One of them is just like this. I'm going to simply ask you in one of your questions, it'll be number 5 on your test, maybe number 6 because I haven't thrown that multiple choice question in yet. Calculate the percent composition by mass of some substance. Okay, so what we're going to do with this is we're going to, well, maybe I should talk more about it before I say what we're going to do with it. A chemical formula deals with the number of atoms that are inside the chemical formula, right? So don't write this stuff down that I'm going to put here, but we would say that there are 6 atoms of carbon. There are 12 atoms of hydrogen. Sorry, the pen's not keeping up with me as I write, so that's why it looks kind of spastic. And 6 atoms of oxygen in that chemical formula. It says nothing about mass. There's nothing about mass because they're not equal. A carbon is a lot bigger than a hydrogen, and an oxygen is a little bit bigger than a carbon. So as far as looking at their ratio of 6 to 12 to 6 does not tell us anything about how much percentage of the substance that they make up. Okay, now let's not use atoms because in this chapter we're all about the mole. So really what I could say is if I had 1 mole of glucose, I could say that there are 6 moles of carbon atoms inside of there, 12 moles of hydrogen atoms, and 6 moles of oxygen atoms inside of there. Now I know how to find the mass of moles. So what we're going to do for these problems, in case everything that I'm saying to you right now, you're like, what is he talking about? These problems kind of follow a procedure, and you're allowed to be a robot with this procedure. What you're going to want to do is do the molar mass thing that I said you don't have to show your work on. This is the part where you are going to have to show your work a little bit. You've got 6 carbons. No, we're not supposed to use red. 6 carbons at 12 each adds up to 72. You've got 12 hydrogens at 1 each adds up to 12. And you've got 6 oxygens at 16 each, adds up to 96, I believe. Add all this together and you have the molar mass of glucose. 180, okay? So what we can say that there's 180 grams per mole for glucose. Of that 180 grams, 72 grams in 1 mole is carbon, 12 grams of 1 mole is hydrogen, and 96 grams of 1 mole is oxygen. So the percent by mass is simply just taking each one of those elements in the substance, its mass, and dividing it by the total mass. And then to make percentages, we just times it by 100. I don't even think I show that when I was trying to make the slides for our next time we meet. I didn't even show the times 100%. I wrote it as a percentage. But when you divide that, you're going to get a percentage. I don't know what that percentage is. How about 40%? Okay, then we do the same thing for the hydrogens. For the hydrogens, we've got 12.0 divided by the full 180 times 100%. My calculator said 7. Yeah, see, I didn't even show the times 100% part of each one of these. And then oxygen, to finish off this example, 96.0 grams out of 180 grams is 53%. I didn't even look forward, did I? You're like, wow, he's a mathematician, a math magician. No, I'm not. What I am is I know that percentages have to add up to 100%. And if carbon makes up 40% of it and hydrogen makes up 7% of it, oxygen makes up the rest of it. So 47 subtracted from 100, I believe, is 53. So that's a way to check your work. You can do all of this, and if all of these add up to 100, then you know that you did it correctly. And there's a little note for it. I probably have one more example because I see there's still 2 more slides. I'm going to go forward. This is the opposite direction. So we're already doing both things. There's the next notes that we do, I guess, would be on Monday when we get back after break, are going to be more of this, like example 2. So this is just basically the opposite direction. So instead of us solving for the percentages, this is the one where the percentages are given. And we do have a lab like this. It's a lab that is worth waiting for when we're together. When we're back together and things are more normal, I'd like to go back and do some of the labs that we skipped over in chapters 1 through 10 that have a little bit of meaning. And even though they might not have any meaning for the chapter that we're in at that point in time, I'm going to make a quiz. So after you do the lab, the next day we'll take a quiz on it. So this will be one of them. What you're going to do for this lab is you're going to take one of two things. You're either going to take magnesium and burn it, or you're going to take magnesium sulfate and heat it. And in either case, you're going to change the composition of what's there. And by taking mass from the beginning and mass at the end, we can figure out the percent composition of magnesium in the first one when it forms magnesium oxide, and magnesium sulfate when you evaporate away the waters that are there. I know, sounds vague. You got to see it, and we'll do it. But that's where we're going to practice this. And those are the experiments that are true experiments that a chemist would do to figure out the chemical formula of something. Now, it's called an empirical formula because when you're dealing with molecules, it doesn't tell us what the actual molecule is. It tells us what the lowest whole number ratio is. So with carbon, hydrogen, nitrogen, and oxygen, there might be some number, you know, the subscript numbers that we put in last chapter, where it doesn't reduce down because molecules don't have to do that, right? Like, for example, we learned how to do like nitrogen dioxide is NO2, but dinitrogen tetroxide is N2O4. Why didn't we reduce that down? Because it's a molecule. When we learned how to like take calcium and oxygen, crisscross those oxidation numbers, that one we reduced it down because that's an ionic solid. So these ones, ionic solids already are empirical formulas, but molecular formulas aren't always empirical formulas. Man, there's a lot to remember in there. It's okay. You follow the procedures, you're going to be just fine. Here's how we do this procedure. We assume a 100%, because if all of these percentages are true, that tells us that all 4 of these percentages add up to 100%. So now what we're going to do is with 100%, let's just pretend that's 100 grams. Because if it's 100 grams, then that means that 27% is 27 grams out of 100. So we can say that there is 27 point, not 2. We're almost done. For those of you getting antsy, got to go to the bathroom, we're just about done. 27.59 grams is carbon, 1.15 grams is hydrogen, 16.09 grams is nitrogen, and 55.17 grams is oxygen. And we're trying to come up with a chemical formula that says CHNO, but there's got to be some subscripts that go in here. We just don't know what they are. Chemical formulas don't tell us anything about mass. They tell us about how many. They tell us that there's 1 carbon to every 1 hydrogen atom, to every 1 nitrogen atom, to every 1 oxygen atom. They tell us that there's 1 mole of carbons to da-da-da-da-da. So these are not masses. Therefore, we can't use these masses. I got to get rid of them. So how do I get out of mass and get into moles? Hey, I know a process for that. It's a 2-step conversion table that says get out of grams, get into moles. Go to your periodic table, 12.0. 27.59 divided by 12 comes out to be 2.3. Do that for all 4 of them. On your test, I'm going to give you 3, not 4. So makes it a little shorter. 1.15 grams of carbon, get out of grams of hydrogen, get out of grams of hydrogen, get into moles of hydrogen. Periodic table says 1.0, 1.15 moles of hydrogen. That's an H, not an A. keep on going because we're having fun. Nitrogen, 16.09 grams. Get out of grams. Get out of grams. Get into moles. Moles. Periodic table says 14. 16 divided by 14, 1.15 moles. Some kind of weird noise going on around here right now. The building is possessed. 55.17 grams of oxygen. Get out of grams of oxygen, get into moles of oxygen. Periodic table says 16.0. Do that division, 3.44. Okay. Now, we're so close. When you look at these numbers, we have to make this a whole number ratio. We never saw a chemical formula that said N2.1, O 4.2, right? They have to be whole number ratios. So if you can look at this and see what the whole number ratio is, some of you can look right at this and say, oh, there's 1 hydrogen to every 1 nitrogen. Carbon is twice as much, so there must be 2 carbons to every 1 hydrogen. And really, we can even see with oxygen that it's 3 times bigger. If it was 3.45, it would be exactly 3 times bigger, but close enough for an experiment. Okay? If you can't tell, what you do is you take each of the numbers and divide by the smallest number that you see. All of them get divided by the smallest number, 1.15. Do that on your calculator. When you do that, your calculator says 2, 1, 1, 3. So now I know that the chemical formula or the empirical formula for this is C2, H1, N1, O3. And then I would need other experiments to tell me what multiple of this is the actual molecule. But we're just starting, so that's all that we know how to do. Thank you for your attention. Those notes took 59 minutes, not bad. We're all, 60 minutes, we're all done. I am going to turn off the recording